Last time, we discussed Fick's law and how flux is related to the derivative of concentration with respect to the position x. We also discussed that this linear constitutive law is fundamentally because the fluid is very controlled. This is not a natural diffusion process that might have many nonlinearities and higher order effects involved. Instead, it is a model of a very controlled process, and we are going to explore what that means today in the context of diffusion in equilibrium. Let's look at our picture of Fick's law again. Again, we have a tank. We have a position x1 and a position x2. The difference between them is dx. We have a tank and two positions in that tank, x1 and x2, that are very close to each other, separated by a distance dx. This dx is going to be small because eventually we're going to actually take the limit as dx goes to 0. By the assumption that the concentration is in equilibrium, that C of x is constant with respect to time, we know that the mass of chemical in the small volume between x1 and x2 is constant. How can we use the fact that f of x1 is equal to f of x2 to understand this diffusion process better? Moreover, how can we use that we know that f of x is equal to minus d dc of x dx times A? We just plug this formula into the equilibrium statement. Minus d dc of x1 dx has to be equal to minus d dc of x2 dx, where I've divided by A because A is on both sides. Now I can factor out d, and I get d times dc of x2 dx minus dc of x1 dx equal to 0. Now, since d is greater than 0 as well, we could divide by that as well. Moreover, now we can do something kind of tricky. We can divide both sides by dx, which is also positive. Really, this is a trick. There is no way you could guess to do this, but we will see later in lecture 16 that this step is actually pretty natural. Now, if we take the limit as dx goes to 0, this becomes the second derivative of c of x with respect to x, giving us the second derivative of c of x with respect to x is equal to 0, where I've divided both sides by d. Now remember, this version of the diffusion equation does not include any reaction or accumulation and assumes equilibrium. Notice that this equation does not depend on c of x, only on derivatives of c of x. Hence, solutions are reasonably easy to guess. What curve has 0 as its second derivative? Straight lines. As an example, if you know that a tank is regulated so that it has concentration on the left, C at x equals 0 is equal to 5, and concentration on the right, C at x equals 1 is equal to 1, then the diffusion equation predicts that the curve will be C of x equals AX plus B. The concentration at x equals 0 is 5, so B must be equal to 5. And the slope between x equals 0 and x equals 1 is negative 4, so A must be equal to negative 4. Hence, the concentration, according to the diffusion equation, will be C of x is equal to 5 minus 4 times x. It'll look like a line that looks like this. It is worth thinking for a moment about what this means physically. The derivative of the concentration with respect to x is everywhere equal to negative 4. Hence, there is flux in the tank at x equals 0. And there is flux out of the tank at x equals 1. We don't know why or how that flux is occurring. We simply know it is occurring. It is probably occurring because of some form of engineered process control. Now think about the small volume we started with. Even though there is flux into the tank and flux out of the tank, the mass of chemical in the small volume really is constant because the flux of chemical into the small volume is the same as the flux of chemical out of the small volume. This is because we took the limit as dx goes to 0. Lastly, what if there was no flux in and no flux out of the tank? then that would mean that D must be equal to 0 because of Fick's law, so the solution would be a flat line. The concentration would be the same everywhere. This is just what we see in my coffee cup, that at equilibrium, the concentration of milk in the coffee is the same everywhere. So what should you remember from today? The diffusion equation in equilibrium with no accumulation is the second derivative of the concentration with respect to position x. When you solve the diffusion equation, you get a prediction of the concentration everywhere in the tank by only knowing what is happening at the edges of the tank. Next time, we are going to talk about what happens when there is accumulation, where for some reason the chemical is accumulating or being taken out of the fluid everywhere.